Welcome to our journey exploring the concept of integration in calculus. Today, we will explore the intuitive meaning, formal definition, and the relationship between integration and antiderivatives. We are familiar with calculating the area of basic geometric shapes using simple formulas. For a rectangle, the area is found by multiplying the length by the width. Its length is 4 units, and its width is 2 units. The area is 4 times 2, which equals 8 square units. This is a circle with a radius of 2 units. The area is pi times the radius squared. That's pi times 2 squared, which equals 4 pi square units. This is a triangle with a base of 4 units and a height of 3 units. The area is half of 4 times 3, which equals 6 square units. Beyond these basic shapes, we often encounter many other forms in the real world. For example, the shape of a bridge, an archway. All of these can resemble curves we study in mathematics. But how can we find the area under such curves? To do that, we need more advanced tools. And one of the most powerful is integration. Now we need to transform the image of a real bridge into its corresponding mathematical function. On our graph is the curve y equals x squared plus 4. You can see how the red area resembles a portion of the bridge, can't you? To calculate the area of this red region, we face a challenge when using traditional area formulas because its boundary isn't a straight line. So how do we calculate the exact area of this region? We'll approach this problem in a familiar way. We'll divide this shape into 4 rectangles. Each rectangle has a width of 1. The first rectangle extends from 0 to 1, the second from 1 to 2, the third from 2 to 3, and the fourth from 3 to 4. We can easily calculate the other side for each rectangle by substituting the x-coordinate to find y. For the first rectangle, when x equals 0, y equals 0 squared plus 4, which is just 4. So the area of the first rectangle is 1 times 4, which equals 4 square units. Similarly, we have the area of the second rectangle as 5 square units, the third as 8 square units, and the fourth as 13 square units. I'll call S4 the total area when dividing this shape into 4 rectangles. We have the total area S4 equal to 30 square units. This is our approximation, but how close is it to the exact area under the curve? Our previous approximation wasn't accurate enough. So we'll divide the shape into 8 rectangles instead of 4. Each rectangle now has a width of 0.5. Continuing similarly, we can calculate the areas of all 8 rectangles. 2 plus 2.125 plus 2.5 plus 3.125 plus 4 plus 5.125 plus 6.5 plus 8.125. We get S8 equals 33.5 square units, which is closer to the true area than our previous S4 equals 30. As we use more rectangles, our approximation becomes more accurate. Let's increase the number of rectangles to 40. With each rectangle now having a width of 0.1, our approximation becomes more refined. When we calculate and sum all 40 rectangles, we get S40 approximately 36.54. Notice how this value is getting closer to the exact area. Taking this process even further, let's consider 1,000 rectangles. At this level of precision, the rectangles are so thin they appear almost as a smooth area. Our approximation S10 to the power of 0 is approximately 37.3 is remarkably close to the exact value. As we continue to increase the number of rectangles toward infinity, our approximation converges to exactly 37 1/3. Now let's consider the general case. Suppose we have any arbitrary function, called f, that is continuous over an interval from a to b. We want to calculate the area bounded by the curve f, the x-axis, and the 2 vertical lines at x equals a and x equals b. The approach remains similar to what we've done before. First, we divide the interval from a to b into n equal parts, creating n rectangles. If we create n rectangles, each will have a width of open parenthesis, b minus a close parenthesis, divided by n. Let's call this width delta x. Then, we calculate the sum of the areas of all n rectangles. With the first rectangle, the area is delta x multiplied by f of x sub 1. The second rectangle's area is delta x multiplied by f of x sub 2. Similarly for the remaining rectangles. When we add all these areas together, we get the approximate area of the shape. We can totally rewrite the formula for S like this. Neat and tidy, right? This elegant formula is named after the German mathematician Bernhard Riemann. It's called the Riemann sum and serves as the foundation for the modern understanding of integration. When the limit of n approaches infinity, as the rectangles become infinitely thin, this sum gives us the exact formula for the area. And to simplify this complex expression, the mathematician Gottfried Leibniz proposed rewriting it as, this elegant notation replaced the cumbersome limit expression with a single symbol, the integral sign integral, making it much more manageable to work with in calculus. This integral formula has a profound connection to antiderivatives. We will explore this relationship in our next video, where I will prove this formula for you. Subscribe and hit the bell so you won't miss any new videos.